Okay, so let's go over a couple things here. The accuracy versus precision. You guys seem to have this down pretty well. Accuracy is how close you are to an accepted answer when something is known, like the density of a metal, and then you're testing it, how close you are to reaching that known answer. And precision is just how close your measurements are to each other. So here, this is often used with bullseyes. Here are a series of bullseyes with some shots taken at them. And as you can see with A, B, C, and D, the accuracy is varying and the precision is varying in each of these cases. So if you had to choose one of these that was accurate, which is close to the accepted bullseye answer, C should be accurate, right? This looks accurate. And then also A is sort of accurate. So this one's accurate as well. The precise ones, the ones that are just grouped close together, B looks precise. These are all pretty well close together. So this is precise, not necessarily accurate. And then also C is precise because they're grouped well together. You seem to understand that pretty good. When we use numbers to signify just how the quality of what instruments we were using in that case. So here is a leaf that we're trying to measure, and here's a ruler. And if we take that leaf and we see that it kind of goes down here, we know it's between 3 and 4, but that's all we know. So the number we use to let people know that our measurement device wasn't great was that we should have we need to estimate one digit past what we can read. So we know it's between 3 and 4. We're going to estimate about 3.5. Those are both considered significant figures. This one was known. Ooh, look at that. And this one, I have no idea how that happened. But and then that one was estimated. And so if you have a better instrument like here, now you can see we have a little bit better way to measure this. We know it's definitely between 8.2 and 8.3. So we know the 8.2, we have to estimate the one beyond that. We'll just use 5 because that's almost too small to see anything anyway. But 8.23, 8.26, all those would have been fine. But these two now are known, and now this one is estimated. So it's the quality of the instrument that the number reflects. And we call all these significant figures. So here's another example, right? We know this is somewhere between 0 and 10. I don't love that that's a 1. That should be a 0, but that means it's ruler 1 is what it meant. So, right, so it's somewhere between 0 and 10. Here's actually even a 5 mark, so we know it's between 5 and 10. So you could only say that this was 8. You couldn't say 8.3 or 8.5 because already that 8 is an estimate. Whereas in this case, now we know it's between 8 and 9. So the 8 is known, so the second one's going to be estimated, and you might say 8.7 or 8.8, something along those lines. And then here, if you have more hash marks, then better known, so you definitely know this is 8.8. And then beyond that, you can say 8.81 or 8.80 or whatever. All right, so the whole point of this is that numbers will communicate the quality of the measurement. Something that has more digits, more significant figures, has a higher quality measurement device than something with fewer. So if this flask was trying to say it's exactly 163.5 milliliters, you can see here it's a 250 mil flask, but there's no hash marks anywhere to figure out where the 100 is and where the 200 is, and on top of that it's a weird shape, so that you can't even really go by how high up the water is because the volume is getting smaller as it goes up. This is not true. That's a lie that it would be able to say that. At best, you could say that that is 100 or 150 milliliters, and that's it. Actually, I guess just one, right? 100 or 2. Anyway, okay. Why is this important? This is important because when we have situations where we're measuring things like this cannonball here that got lodged in the cannon, the supervisor probably told his worker that that cannonball needed to be a 9 centimeter diameter cannonball. Well, that's great, but the problem is when you're making cannonballs and you get one that's like 8.9 centimeters and 8.7 centimeters and 9.1 centimeters, you would call all those 9 centimeters. What the person should have said, it needs to be 9.0 centimeters, which means now this one gets rejected. And because it would be rejected with more significant figures and not rejected with fewer significant figures, it wouldn't get lodged in there when it was shot and then hence break the cannon. So the quality of what you are measuring can be important, and in this case could save lives. All right, so here are the rules for significant figures. These are very ruly. If you like rules, you can write these down. But if you don't write a zero, it's always a significant figure. So anything that's not a zero, all these numbers, 9, 8.9, 8.7, right? 100, that's not a good one. But yeah, 2.7, they're all non-zeros. So non-zeros are always significant. Sandwich zeros are going to be significant. So basically, if you're in between two significant numbers, then you are significant. Leading zeros are never significant. Leading zeros aren't, because you can just as easily represent this number as 4 times 10 to the minus 4. And those zeros are just letting you know you got to move those decimal places, just like this 10 to the minus 4 is telling you the same thing. So leading zeros are never significant. And in Puerto Rico, there's a saying that basically says you are a zero to the left. It's an insult to mean that you're useless or insignificant. All right, trailing zeros are a little more confusing. Sometimes they are, sometimes they aren't. If they come after a decimal point, they are considered significant. If they come, it's in this case where there is no decimal point, they're just holding a place like the ones were in the leading zero case. So this could be just as easily 3 times 10 squared, right? So those zeros are just letting you know you have to move the decimal. These zeros are unnecessary in that regard. They're just trying to let people know you measured to that extent. And then another thing which becomes more important when we do multiplication is this rule here, that doing conversions, anything that's a definition, anything that's a count, those are considered infinite significant digits. So even though 12 equals a dozen, that should have 2 significant figures, that should have 1 significant figure. The reality is they both are considered infinite significant figures. And we'll get into that a little bit more later. But here, 1,000 millimeters equals 1 meter. This one has 1 significant figure. That one has 1 significant figure. But they shouldn't hold back what it is that you're measuring, because that is a definition. That's infinite significant figures. So when you do some multiplication or something, you shouldn't use this as the determiner for how many significant figures you use. All right. So another way to remember all these rules is this Atlantic-Pacific rule, and this simplifies it significantly. People seem to be familiar with the idea that there's an Atlantic Ocean on the East Coast and a Pacific Ocean on the West Coast. So if a decimal is present, like the Pacific Ocean, P present, you start from the Pacific Ocean side. When you see a non-zero, you start counting, and then you continue to count to the end of the number. So in this case, 1 is not a 0, so there's a decimal present. So we're going to start from this direction. 1 is not a 0, so that's the first, second, third, fourth. This has 4 significant figures. If we had something like 00318, right? Decimal present, so we're going to come from the Pacific side. 0, so that's not it. 0, that's not it. This is the first significant figure. 1, 2, 3. So this would have 3 significant figures. If the decimal is absent, so if you have no decimal, as in this case, you come from the Atlantic side. Absent and Atlantic both start with A. The first non-zeros where you start counting, and then you keep counting as you go that way. So that's a 0, so we don't start there. That's a 0, we don't start there. This is a 5, that's where we start. 1, 2, 3. So that has 3 significant figures. Likewise, if we had 1010, no decimal, we're going to start from the Atlantic because it's absent. This is a 0, so we don't count that. That's a 1, so that's the first one. That's a 0, but it came after that one, so it's significant. And that's a 1, so that's significant. So coming from this direction, you just keep going till you get to the end of the number. Now, this is actually why we use scientific notation. Scientific notation is something of the best way to show everyone what you have. So let's say this number, the 101.0. So 1.01 times 10 to the 2/3, right? So all your significant figures when you use scientific notation are right here, and you just count what's there and you're done. So this one, that would be 3.18 times 10 to the minus 3, right? 3 significant figures, because they're all right there in front of the 10. So when you do scientific notation, you don't count the 10 power as part of the significant figures, but all your significant figures are located right in the front. So you don't have to worry about it as far as figuring out the rules and all that. All right. When we do calculations, you know that a chain is only as strong as its weakest link. And that's true with significant figures. And we try to do a lab to express this to you. If you have certain numbers that are weaker than others, you have to let the answer not be stronger than the weakest. So let's look here. This 12.51 has 4 significant figures. This has a decimal present, so we're coming from the Pacific. That's 0, so we don't start counting to the first non-zero. So this has 1, 2, 3, 3 significant figures. This one has 4. So when you put that in a calculator, you get this huge number, and this huge number has 1, 2, 3, 4, 5, 6. That has 6 significant figures. But your answer can't have 6 because it was made up of something with 4 and 3. So this can't be more accurate than what was brought in there, or more precise, or basically of higher quality than what you started with. This is the lowest quality number, 3 significant figures. So our answer has to have 3. So we got to cut it off here and make it 3 significant figures. And that is why we round in significant figures. And we did this lab where we were measuring something, and you saw why this is. You can use an Erlenmeyer flask to fill a graduated cylinder, and the Erlenmeyer flask isn't as good, isn't as high of quality. So multiplying by all the Erlenmeyer flasks that you're putting into a graduated cylinder doesn't make it more accurate. The answer is going to be less accurate. So here, looking here, we have decimal present coming from the Pacific side. That's a 0, so that doesn't count yet. This is our first non-zero, so that's 1, 2, 3. Even though this is a 0, it's after we started counting, so we count it. So that has a total of 4 significant figures. This has 2 significant figures. When you divide them, you get this number, which has a whole bunch of significant figures. But our weakest number, our weakest link was this one. So we got to cut it off at 2. So our answer should only have 2 significant figures, which is as many as our weakest link. So again, remember, this is trying to stress that numbers communicate the quality of the measurement, and you can't have a number that's communicating great quality of measurement, even though what was put into it were these low quality measurements. Same thing here. You can't have a high quality measurement number when what was put into it were lower quality measurements. All right, there you go. That's that. I hope that helps, and I will talk to you guys